Imagine you have a data set and you want to group them together based on some notion of similarity. Looking at this data, we can clearly see that there are 5 distinct groups. And after looking at this data, we could sit for a while and assign the groups to each data point manually. But this is not something that we want to do. We can use an unsupervised machine learning technique called clustering to automatically find the groups and assign a label to each sample in the data. In particular, we'll focus on a very popular algorithm called k-means to automatically cluster our data. In this video, we'll go through the following topics: how we visualize the data, how to use k-means algorithm implemented in Scikit-learn library, understand how k-means algorithm really works, and finally, how to implement k-means from scratch. First, we'll import some libraries that will be used, like NumPy and Pandas, and I'm also using a relatively new library called Let's Plot to visualize the data. Next, we'll focus on dataset creation. Here, I'll be generating a synthetic data for this demo, as it makes it easy to show how the clusters actually look like and how the predicted clusters look like. I've created 1000 samples where each sample has 5 features. Also, I've specified that there should be 3 clusters as indicated by the centers parameter. If you are clustering textual data like news, articles, tweets, etc., you will probably use classic NLP based feature extraction techniques like TF-IDF or word2vec. Recently, deep neural network based language models are also frequently used as feature extractors for textual data. Common language models include BERT and OpenAI embeddings. Similarly, you can also cluster images. Deep neural network models are commonly used to extract embeddings from images, which can be used to cluster them. If your dataset is tabular in nature, then also it is applicable for clustering. You have to make sure all your features are numerical and scaled or normalized properly. For example, you could have a dataset of users which you want to cluster. Each user could have features like age, salary, height, etc. And based on these features, you can cluster them. Just remember to scale or normalize your features. Next, we focus on dimensionality reduction and visualization. While clustering, visualization is a must. Since clustering is usually performed on unlabeled data, there isn't much we can do to evaluate these algorithms. So we must visualize our data to understand it. Since our data can be high dimensional, it is not possible to visualize them unless it is 2-dimensional or 3-dimensional. In our case, each sample is a vector of 5 dimensions. So we need to convert this 5-dimensional data in 2 dimensions so that we can plot it. This is called dimensionality reduction, and there are several methods that we can use. But here we'll use PCA or principal component analysis. We'll fit this PCA with our data so that we can later transform our 5D dataset into 2D. For plotting the data, here I've defined a helper function to visualize. First, we reduce the dimension into 2 dimensions and then use it to plot. The remainder of the code is specific to plotting, which I won't go through here. Let's run this to visualize the data that we just created. We can clearly see there are 3 clusters and each data point is colored according to the cluster it belongs to. The cluster center is indicated by the big plus sign in the middle. Now let's implement this using Scikit-learn. First, we import the k-means class from scikit-learn.cluster and instantiate it. For k-means algorithm, we need to specify how many clusters we want it to create. This is indicated by the n clusters parameter. Since we know there are 3 clusters in our dataset, let's put 3 as n clusters for now. We'll later see how we can detect how many clusters are appropriate for any given dataset. Choosing the number of clusters is crucial and is mostly driven by application. For example, if you want to cluster users into different segments, then your choice will be driven by marketing strategy, for example. To train this model, we can call fit function or we can call fit predict to run the algorithm. The fit predict will fit the model and also return the labels for each data point. After training, we will now plot how the cluster looks like as well. It seems to have done a great job. The clusters are nicely separated and the cluster centers also closely match the actual cluster center. Of course, in real world, it won't be this easy and you will typically play with the number of clusters and different parameters of the algorithm. Now let's focus on finding the number of clusters for our dataset. In practice, we will know beforehand how many clusters to create, and the data points also aren't as neatly separated as the synthetic dataset. Let's imagine we didn't know that there were 3 clusters. One algorithmic way to determine number of clusters is called elbow method. Basically, we run k-means algorithm with different number of clusters and keep track of a field called inertia. The idea is to select the cluster where the inertia starts to flatten. Now let's run this code. As we can see from the plot, the inertia drops quite a lot from 2 clusters to 3 clusters. But from cluster 4 onwards, it is relatively flat. So we choose 3 as the appropriate number of clusters. Notice the shape of the plot here. It looks like an elbow and hence the name elbow method. Or how does k-means algorithm really work? It is quite simple. The idea is if we know the cluster centers, then we can find closest point to each center and assign a label. And if we know the labels, then we can compute the cluster center for each label by taking the average of each feature of the data points belonging to that label. So here is how it is implemented. First, we randomly choose cluster centers from the dataset. Then, for each data point, we'll find which is the closest cluster center. We'll use matrix multiplication to find dot product between all data points and its cluster center. Then for each data point, we'll take the cluster with highest dot product to be its label. Now that we know the cluster label for each data point, we can compute new cluster centers by taking average of all data points in a given label. We repeat this process until cluster centers do not change or up to maximum number of steps. For simplicity, I didn't check whether the cluster centers are changing or not. So we'll just run this up to the number of steps specified. In some cases, there can be less number of clusters formed than we want. In that case, we just restart the whole process. The predict function is also very simple. We just compute the dot product of the input data with the cluster centers and return the index of most similar cluster center as its label. Now let's run this and plot the clusters. K-means is quite sensitive to the initial selection of cluster centers. So we might have to run this multiple times to get good results. As we currently see, all of the cluster centers are in the right hand side. After running for a few times, this is what we have. I've left out a lot of details in the implementation about efficiency, convergence, and accuracy, but main idea of k-means has been implemented and should be a good starting point if you want to explore further. This is all I wanted to showcase. I hope you found this video useful. Thank you.